Welcome friends, Igor is here, and in this video we will connect the span construction with the null spaces. In this lesson we will discover that the null space of a matrix can be described using the span construction, and we will learn how to describe spans in a more efficient manner. Let's get started. Let's go back to a known problem of computing the null space of a matrix. So we are given a matrix A and we would like to compute its null space. We know that the null space of the matrix A is the solution set to the homogeneous linear system with A as the coefficient matrix. When solving homogeneous linear system, it is sufficient to reduce only the coefficient matrix because the last column, the vector of constants, the zero vector, will always remain the zero vector no matter what row operations you apply. So this is what we do in this case. We find the reduced row echelon form of the coefficient matrix, and we see that we have two free variables, x3 and x5, and three dependent variables, x1, x2, and x4. We express each dependent variable in terms of the corresponding free variables, and we obtain the vector form of a solution vector. This is where we would normally stop, but now let's take our computation one step further. Here's what I'm going to do. I'm going to represent this solution vector as a sum of two column vectors, and you see the pattern. In the first vector, I gathered everything that involves x3, and in the second vector, I gathered everything that involves the free variable x5. And then we can factor out the free variable from each of these vectors because every component in the corresponding vector is multiplied by this same free variable. This tells you that a typical solution to this homogeneous linear system looks like a linear combination of these two fixed vectors, where the variables x3 and x5 are used as scalars to construct the linear combination. Let's denote each of these vectors by some letter. So let's say the first vector is the vector z1 and the second vector is the vector z2. Then the entire solution set to the homogeneous linear system, which is the null space of the matrix A, can be described as follows. It is the set of vectors of the form x3z1 plus x5z2, where z1 and z2 are the given fixed vectors, while x3 and x5 are free variables. In other words, they are free to assume any possible values. But I hope you recognize this description as the construction of a span. This is precisely the set of all possible linear combinations of the vectors z1 and z2, and so this is exactly the span of a set which consists of two vectors, vector z1 and vector z2. This example illustrates that the null space of a matrix can be expressed as a span of a certain set of vectors. Moreover, notice that in this example, the number of vectors to construct the span was equal to the number of the free variables in the infinite solution set. In the second example, we are going to see that it is possible to describe the same span using fewer initial vectors. Let's start with a 3x4 matrix B. We reduce this matrix, and this tells us that the homogeneous linear system with B as the coefficient matrix has infinitely many solutions. x3 and x4 are the free variables, and x1 and x2 are the dependent variables. Now, let's construct a particular solution to this homogeneous linear system by assigning values to the free variables. And in this case, I'm going to assign a 0 value to the variable x3 and value of 1 to the variable x4. Then x1 must be equal to 2 and x2 must be equal to 3. We know that solutions to linear systems are linear combinations of the columns of the coefficient matrix that are equal to the vector of constants. So we have this particular solution of the homogeneous linear system, and therefore the components of this solution vector can be used as scalars in the linear combination of the columns of the coefficient matrix B to produce the vector of constants, and the vector of constants in a homogeneous system is the zero vector. Now we are going to use the columns of the matrix B as a set of the column vectors, and I will denote these vectors by W1, W2, W3, and W4. We have a set T of 4 column vectors. They come as columns of the given matrix B. Using this notation, we can rewrite the equation at the top of this slide as follows: 2W1 plus 3W2 plus 0W3 plus 1W4 is equal to the zero vector. What we are going to do next is we are going to take this vector equation and solve it for the vector W4. Let's pause for a second and realize what this means. This equation tells us that the vector W4 is a linear combination of the vectors W1 and W2. Therefore, whenever we encounter the vector W4, it can be replaced with a linear combination of the vectors W1 and W2. Here is a visual illustration of this idea. Let's take an arbitrary linear combination of the vectors W1 through W4. I just took some random scalars in this linear combination. This linear combination is equal to the following expression, and this is because we can replace the vector W4 with the corresponding linear combination of the vectors W1 and W2. But now this long expression can be written as a linear combination of vectors W1, W2, and W3. Let me show you why. First, we use the distributive property of scalar multiplication over vector addition, and then we use the associative property for scalar multiplication. Then we use the commutative property of vector addition and distributive property for scalar multiplication over vector addition. But now you see that we started with a linear combination of vectors W1, W2, W3, W4, and we were able to get rid of the vector W4 in this linear combination. This linear combination, in fact, can be written as a linear combination of only 3 vectors, W1, W2, and W3. Of course, this kind of procedure can be performed on any linear combination of these 4 vectors, and therefore what it means is the following. Any linear combination of the vectors W1, W2, W3, and W4 can in fact be represented as a linear combination of only 3 vectors, W1, W2, W3. You don't really need the vector W4. Now, because the span is the set of all possible linear combinations, this tells us that the span of the original set T of 4 vectors is equal to the span of only 3 vectors. Vector W4 was excessive. We don't need it to construct the same span, the same set of all possible linear combinations. Let's take this one step further. Let's construct another particular solution of the homogeneous linear system, but this time I'm going to switch the roles of the free variables. I'm going to assign the value of 1 to x3 and the value of 0 to x4. This particular solution results in a linear combination of the vectors W1 through W4 that is equal to the 0 vector. And notice that because we assigned 0 value to the free variable x4, the vector W4 is multiplied by the 0 scalar, and therefore it's not explicitly present in this expression. Now, what we do is we solve this vector equation for the vector W3. You see what it means? The vector W3 can be expressed as a linear combination of vectors W1 and W2. In turn, it means that whenever you have a linear combination that involves vectors W1, W2, and W3, in fact, it can be rewritten as a linear combination of vectors W1 and W2 only. This means that the span of vectors W1, W2, W3 in fact is the same as the span of the set of only 2 vectors, W1 and W2. Let's recap what we achieved in this example. We started with a set T of 4 column vectors. then we showed that you do not need the vector W4 to construct the same span. And then next, we showed that you do not actually need vector W3 to describe the same span. So we started with a span of 4 vectors, and we showed that the same span can be constructed using only 2 vectors. Moreover, it is not yet clear why, but we cannot continue this reduction. We cannot throw out either vector W1 or W2 and obtain the same span. In a sense, we have achieved the most efficient representation of a span. We will understand the reasons for this and what's really going on behind the scenes here in the future lessons. But for now, let's just observe that the 2 vectors we kept, W1 and W2, corresponded to the pivot columns in the reduced form of the matrix B, and the vectors W3 and W4, which we were able to dismiss, corresponded to the non-pivot columns of the reduced matrix. This is not a coincidence. Why it is not a coincidence? We will figure out later once we define the notions of linear independence of column vectors. If you found this video useful, please give it a like to help others discover this content, and subscribe to this channel to see future videos. In the next video in this series, we will define the notions of linear dependence and linear independence. I will see you later.